All right, hey everyone, welcome to week 51 of Chill Kernel Hacking for Fun. Thanks a lot for joining. We are almost at 1 year of weekly kernel hacking, which I'm pretty excited about. This week, we are, I don't even have my browser tab open. This week, we are continuing, or rather starting Lab 5, which is the file system lab of the MIT course that we are following. Last week I planned to start this, but I ended up getting sidetracked because I forgot that every time I switch labs, I need to merge in a bunch of foreign code. And that code merge always causes breakages. So that's what I debugged last week in week 50. And now we are here for week 51. At least I'm pretty sure it's week 51. Let me just quickly check. Yeah, last week was week 50. We're here week 51. Welcome to anyone joining the chat. I'm going to quickly do my regular set of tests to make sure everything is going, such as my test 0 post to make sure the chat widget is working. Yeah, welcome to anyone joining the chat. Today's file system day. So if I remember correctly, I got things working. I fixed the boot breakage and got my kernel booting again last week. So this is what it looks like. So now I'm able to run programs again. Yeah, what's up, Bishwaz Plays? Good to see you too. What's up? I'm doing pretty well. I'm having a nice Sunday. The weather's good here. And I'm super excited about what we're going to work on today. File system stuff. Yeah. Hope you had a good week. How are you doing, Bishwaz Plays? Yeah. So first, before I get started, I'm just going to quickly go and check my Git history. So I kind of decided to, I'm doing a bit of a different branching strategy. Previously, I just had like a lab 3 branch, and then when I started lab 4, I would merge lab 3 into it. But now what I think I'm gonna do is just have this like dev branch and merge the labs into it, because that makes it easier to debug the breakages. But first, actually, I need to clean up this history a little bit. So a couple of things we don't need anymore. We need this stuff. And here's also my random Python script that I used to generate the page tables last week. Because that was the problem last week, was the kernel got too big and it exceeded the 4 megabytes of space we had mapped in the early boot era, I guess, or the early boot phase. I don't think this is really worth keeping around, so I'm going to delete it. So now let's take a look at what some of these other things are. Okay, so here I have commented out a few things, but then I think I reverted it. So I'm going to hop into lazy git for these changes. So I have a commit that comments out some stuff which I thought might have caused the breakages. Here I am, and then I revert that. So I think I can just simply delete both of these. Then I have this temp fix thing, which temporarily fixes the problem by simply reducing the size of the kernel. That was a bit of a band-aid solution. I later did a production fix. So what I'm going to do is I'm just going to check back out here for revert. I'm going to drop these two, and then I'm going to drop this one and this one. And then I'm going to, so now I've dropped those pairs of random stuff and reverts. Here's a random panic that I don't need anymore. So now I've kind of cleaned up the history, and this is a bit random. And then I will also call this fix also. So now I have my nice set of fixes. This was lab 4, I think, yes. And now we're ready for lab 5. Cool. And we have a bit of temporary patches in order to make the kernel run as instructed by this exercise. It says you will need to comment out this thing and also this thing for the moment. If your lab code doesn't contain any bugs, the test cases should run fine. Don't proceed until they work. Don't forget to uncomment these lines. Maybe I will just run. Ooh, wait, I do not want that. Maybe I'll just run grade lab 4 quickly to make sure that still passes. I think everything should still pass. I'll just clean up. All right, what the hell? Okay, that's a bit odd. Okay, interesting. So that's a bit odd. I'm not super stoked on that. I'm just gonna commit these as a temp. And then I'm just going to check back out to lab 4. Oh man, you have got to be kidding me. Wow, did really something else break? You have got to be kidding me. Okay, so it's pretty clear that these are working in the lab 4 branch. So that means something went off the rails. So if I run it at the tip here, now we start having all sorts of failures. That's annoying, okay. That is very annoying. But at least we are now a little bit better positioned to try to understand the source of those failures, because now we can view the merge diff and see all the new code that was apparently introduced, although I kind of don't really understand what could have changed. Did they really change that much? Also, did they comment out? Yeah, they commented out a C printf. So I think this thing is complaining about it's missing a bunch of printfs, which I think they just commented out, maybe. Yeah, they just like commented out a bunch of stuff, which is why the tests no longer pass. That's kind of stupid. All right, I'm just going to temporarily revert some of these changes. I think I'm going to show you a way to do this with lazy git, which I think is pretty awesome. So here's the situation. I have this commit that merged a bunch of code into my kernel, and now my tests are no longer passing. But it's not because the code broke things. It's because the code simply commented out a few of these print messages, which the tests were using to make sure things were working. So all I want to do is temporarily revert some of these things. So in lazy git, I'll go to the commit and search for this env file. And then now I'm going to make a temporary patch like this. So here's the hunk, and I'm going to add this to my custom patch. And I think the other one that was relevant was syscall.c. So now I'll come here to syscall.c and also add that to my custom patch. So now I have a few things in my custom patch, I think, although I'm actually having a few things in my custom patch, and I think that's it. So what I'm going to do is apply the patch in reverse. Apply the current patch in reverse to the working tree, which is, check this out. So that's what it did. It applied my patch in reverse. So now it re-enabled those lines that were commented out. And in this case, this one was completely deleted. So now it's being added back. And now, see, it was complaining about we're not having these messages that say new env, exiting gracefully, free env. And now we're adding those back. So I am hopeful that the tests should be passing again. Otherwise, it's a little bit obnoxious of them to just break the kernel like that. I think that improved the situation. We're still missing some new env lines. That's all. That's got to be right. That's right here, I think. So I think there must have been. Yes, it was right here. No, free env. No, it was new env. So it's the same situation, and so I need to once again. So I'm just going to drop these things. They're still my custom patch is still active. Free env, new env, right? So now I want to do the same thing, apply patch in reverse. So now it has we've enabled these couple of things. So now the tests should pass. That looks better. That looks much better. Okay, so now our tests are passing. So now we are really in a state to continue. I'm just gonna let these continue to run while I re-enable sequence to make for tests pass again. Okay. So we have some new code. I was already looking through it last time. So we have a driver, like a very basic disk driver, apparently for this super old disk protocol. It doesn't even use interrupts. It uses port IO with a block cache. And somehow it's actually making use of user level page fault handling, which is kind of interesting. And we have the actual file system code. And then we have this file system server, which is kind of interesting. And we have code apparently for exposing file descriptors and these kinds of concepts to user space. And then we have apparently some different implementations behind the file descriptor abstraction. So a file descriptor can represent an actual file on disk, or apparently it can correspond to an IO stream or like a console type. So we have some code for that. And then apparently we have this spawn thing. Okay. Apparently primes failed. Everything else succeeded except for primes, which is missing a couple output lines, I think. Wow. I'm not sure if that's serious or not, actually. So what is the primes test? Or grade at 4. Test primes. 4 CPUs. All the rest ping pong succeeded. Interesting. So what's going on here? Good. Missing CPU. 2. It's like missing all of these, apparently. Just curious, what does the make run? What does this even look like? Everything is happening on CPU 0 for me because I didn't run it with CPU 4. Stop online. Right. So what happens if I use 4 CPUs? So we actually are getting a lot of these CPUs. Oh, I think, maybe this is the problem. I added a new line here, I think. I thought I was fixing something, but I added a new line. Maybe that's bad for the test. Let me just comment all of these out and run the tests again. Ooh. Kill chemo. Yo, what's up, the bad spy? Finally able to catch the stream. How's it going? Yo, it's good. Thank you for joining. Okay, now the stream's going great. I've been having a bit of an annoying time getting everything working again after I switched to the file system lab, which changed a bunch of stuff. But now I can very confidently say that I am ready to start the file system lab. Yeah, thanks for asking. Thank you to the 6 people in the chat right now. Thanks for tuning in. Just as a bit of a curious thing, so I've been streaming kernel dev for about a year now, but I'm kind of curious if people are interested in certain topics about operating systems. So if you are, feel free to leave that in the chat. Yeah, I'm starting file system work right now, but there's a lot of other areas I could work on, like virtual memory or the boot process or architecture support or stuff like that. Okay. So the file system you're working with is much simpler than most real file systems, including that of x86, but it is powerful enough to provide the basic features: creating, reading, writing, and deleting files in a hierarchy. We're developing a single user OS, which provides sufficient protection sufficient to catch bugs, but not to protect mutual users. We don't support file ownership or permissions. File system also currently does not support hard links, symbolic links, timestamps, or special device files. On disk file system structure. Most Unix file systems divide available disk space into 2 main regions. I think this will be, I'll get out my illustration area. We might need some illustrations today. And today is the 19th. We are on 51. So here we go. All right, so we have disk space and it's divided into 2 types of regions: inode regions and data regions. File systems assign 1 inode to each file in the file system. A file's inodes hold critical metadata about the file, such as its stat attributes and pointers to the data block. So it's basically a metadata structure. The data regions are divided into much larger data blocks, 8K, which within the file system store file data and directory metadata. Directory metadata, interesting. To its data blocks. Directory entries contain file names and pointers to inodes. Contain file names and pointers to inodes. A file is said to be hard linked if multiple directory entries refer to that inode. So maybe an illustration. So this could be like a file. We have like directory entry. Basically, entry. And these things can point to a file, basically. And these directory entries are into different directories. With some other directory entries. Since our file system will not support hard links, we do not need this level of indirection, and therefore can make a convenient simplification. Our file system will not use inodes at all. Interesting. a pointer to an inode. So this is a file inode, which is basically a structure, and then like file data can be you know, in other places on the file system, and somehow there are pointers to these things. Something like this. What's up, AJ? How are you doing? Thanks for joining. So an inode is like a kind of central place. Different things can point to an inode. There's one inode per file, strictly. And then there can be multiple directory entries that point to an inode if you support hard links. And I'm just trying to understand exactly this part. Since our file system does not support hard links, we do not need this indirection, and therefore can make a convenient simplification. Our file system will not use inodes and will simply store all of a file's metadata within the directory entry. So basically it's saying this is kind of how traditional FS. And so in this thing, the directory entry doesn't directly point to the metadata. It says the inode contains system won't use inodes. We will simply store all of a file's metadata within the directory entry describing that file. So instead of doing this, I think it's something along the lines of, so we're not going to have this kind of double pointer aliasing thing. So we can just delete this, and metadata is stored here. Data is not stored here. But here, it's like the metadata is stored here. I wonder if this includes, so we're not even, so we're like, I wonder if that means this thing contains the pointers to the data. Something like this. We just don't have this intermediate layer, basically. Both files and directories logically consist of a series of data blocks, which can be scattered throughout the disk, much like the pages of a virtual environment's address space can be scattered throughout physical memory. The file system hides the details of the block layout, presenting interfaces for reading and writing sequences of bytes at arbitrary offsets. The file system environment handles all modifications to directories internally as part of performing actions such as file creation and deletion. The file system does allow them to read directory metadata directly, which means that user environments can perform directory scanning operations themselves. Read. Rather than having to rely on special system calls. The disadvantage to directory scanning is that it makes programs dependent on the format of directory metadata, making it difficult to change the layout without changing or recompiling application programs as well. So apparently we expose the raw directory like structures or something directly to applications. Most disks cannot perform reads and writes at byte granularity. And sectors. Sectors are 512 bytes each. File systems actually allocate and use disk storage in terms of blocks. Be wary of these two. Sector size is property of the disk hardware. Block size is an aspect of the operating system using the disk. A block size must be a multiple of the sector size. We use a block size of 512 bytes, the same as the sector size. Most modern file systems use a larger block size because storage space is cheaper and it's more efficient to manage storage at larger granularities. Our file system will use a block size of 4K, conveniently matching the page size. Nice. I'm going to take a quick 20-second break, stand up and stretch. Be right back. Okay, so we are learning about some file system stuff that is cool. File systems typically reserve certain disk blocks at easy to find locations on the disk, such as the very start or the very end, to hold metadata describing properties of the file system as a whole. Block size, disk size, metadata required to find the root directory, the time the file system was last mounted, the time the file system was last checked for errors, blah, blah, and these are super blocks. We will have exactly one super block, which is always at block 1 on the disk. Its layout is defined by this thing, struct super. Block 0 is typically reserved to hold bootloaders and partition tables. So file systems generally do not use the very first block. Many real file systems maintain multiple superblocks replicated so that if one is corrupted, the other superblocks can still be found. Or apparently we're not doing that. So there's like a disk. First block is unused because probably other stuff you'll use it. So then we have ours in the second block. Okay. I'm going to copy this diagram because it's probably important. The layout of the metadata describing a file is described by struct file. This metadata includes the file's name, size, type, and pointers to the block comprising the file. Size. We don't have inodes, so this metadata is stored directly in the directory entry. Unlike real file systems, we will use this one file structure to represent file data as it appears both on disk and in memory. What does that mean? The abstract array struct file contains space to store the block numbers of the first 10 blocks of the file, which we call files direct blocks. For small files up to 40K, this means that the block numbers of all of the file's blocks will fit directly in the file structure. For larger files, however, we need a place to hold the rest of the block numbers. So this is basically an optimization, actually, that they're choosing to implement. It's a little bit similar to the small string optimization or stuff like that in C++, where you have some structure that describes a variable length amount of data, and the most naive implementation is you basically always have the structure and then a pointer to the data, no matter how big the data is. But as an optimization, maybe you can reserve a bit of space in the structure, and if the data is really small, it can just directly fit in that structure, and you can avoid an extra allocation of this variable length data field, which can be simpler and faster and avoid indirections. So it's a performance optimization. Okay, so apparently we have some inlining of the data possible. Okay, but apparently if it's larger than that, then we need to overflow into the variable length. Right, for any file greater than that, we allocate an additional disk block called the indirect block to hold up to 1024 additional block numbers. Our file system therefore allows files to be up to 1034 blocks, which is 1024 plus 10 indirect, or just over 4 megabytes. To support larger files, real file systems typically support double and triple indirect blocks. This is kind of funny because it's very similar to virtual memory. It's a little bit like our page tables. Kind of. A little bit. Yeah. I guess the difference is, well, actually, yes. I mean, I was going to say the difference is that files kind of linearly fill up the space, whereas page tables can kind of have random pieces be mapped, but that's actually not true. In file systems, you can have holes in the file, which really makes that abstraction very close to virtual memory mapping. Okay. Directories versus regular files. A file structure in our system can represent either a regular file or a directory. These two types of files are distinguished by the type ID in the file structure. Let's take a look at some of these structures. So we have struct super dang. I would have thought I could do this. Super, it's just super, okay. So we have the super block, which looks like this. A magic number of blocks on disk, and a struct file for the root directory node. So then this file is kind of important. It has file name, some stuff. It has this array of direct and then an indirect block. And so this is like a block index, because so we're using 32-bit numbers. Yeah, pad out to 256 bytes. Must do arithmetic in case we're compiling. Wow, this thing is like dynamically computed. That is quite interesting. So we have a bunch of padding to manually pad this out to 256 bytes, or half a block. Interesting. Okay, so these are some of the data structures we are working with. We have this type field. There's probably an enum somewhere. I don't see it. I was expecting an enum somewhere for all the different file types that are possible, which is just 2. Okay. Contains a file structure. Where was I? So a file can... Actually, there's one thing I didn't understand here, so I'm going to capture that in my board, because I probably will need to understand this later. More shapes. Question. Dang. Okay. Just gonna draw that in there. Okay. So, right. This makes sense. Yeah, sorry this is a bit dry. I'm like, it's always a bit like this when I start a new topic. There's a lot of stuff I need to read in order to have the base understanding of what we're doing here. But then I'll get into the coding after that, which is exercise 1. I just need to read through the rest of this. Hopefully it shouldn't take too much longer. Yeah. Okay. Superblock. The file system manages regular files and directory files in the same way. It does not interpret the contents of the data blocks associated with regular files at all, whereas the file system interprets the contents of a directory file as a series of file structures. Now that is interesting. The data blocks of a directory are actually file structures. Interesting. Yeah. Which means there's like some maximum to the amount of files you can have in a directory, because the file size is limited to like what, 4 megabytes. So it's like 4 megabytes divided by the size of the struct file, basically, is the maximum amount of files possible in a directory. Superblock contains a file structure that holds the metadata for the file system's root directory. So it's a file, even though it's called, it's a directory, even though it's called file. Contents of this directory file is a sequence of file structures describing the files and directories contained located within the root directory of the file system. Any subdirectories yeah, this stuff is pretty interesting. Have my own OS project, but I haven't touched this stuff at all. That's cool, yeah. That's cool that you have your own OS projects. Yeah, I'm always pretty impressed with people that have these. School, and the limit on XT4 is 65,000. Yeah, it's interesting. I don't like, it's not something I think about very much because I don't deal with massive numbers of things in directories. But yeah, like files and directories have limits to how big they can be, in theory, and whether that's a problem in practice is a separate question. But I guess that's kind of interesting. That might be how you explore some fun edge cases in file systems, and maybe there's some fun bugs to find. Okay, the goal is to not have you implement the entire file system, but only implement certain key components. Yo, Digitalized, what is up? Today we're working on the file system. I'm pretty excited about that. Thanks for popping in. Okay, so the goal is apparently to not write the entire file system, but to implement only key components. In particular, you will be responsible for reading blocks into the block cache and flushing them back to disk, allocating disk blocks, mapping file offsets to disk blocks, and implementing read, write, and open in the IPC interface. Interesting. I wonder how that works. I also hope my IPC interface works. I have all the tests passing for my IPC interface, but I think they weren't actually that comprehensive. and didn't test some of the shared memory features that we implemented. And I think those will be important. Knowledge is very limited, so it should be interesting to see. Yeah. I mean, I am also not really an expert on a lot of this stuff, as usual. So I'm learning as I go. But yeah, this is a pretty interesting website to read just about some basic ideas behind file systems. I mean, at the end of the day, you want to create this, you just want to store data on disk, basically. And yeah, so you have data structures to do this, and it actually resembles virtual memory data structures quite a bit, like page tables and stuff like this, quite a bit. I have a suspicion that that will become relevant later. Because you'll not be implementing all of the file system yourself, it's important that you familiarize yourself with the provided code and interfaces. The file system in our OS needs to be able to access the disk, but we have not yet implemented any disk access functionality in our kernel. Instead of taking the conventional monolithic strategy of adding an IDE disk driver to the kernel, along with the necessary system calls to allow the file system to access it, we instead implement the disk driver as part of the user level file system environment. What does that mean? Okay. We will still need to modify the kernel slightly in order to set things up, so the file system environment has the privileges to implement disk access itself. So this is already super weird. I'm really interested to see what this means in practice, but this is pretty different from the conventional approach, at least in my understanding, where in the conventional approach you have like a disk driver that runs in kernel mode, and then it abstracts away the low-level operations of interacting with the disk. And then you have like system call, like, I mean, the file system is also implemented in the kernel, I believe, at least with a typical monolithic kernel design. Maybe in microkernels and other stuff, you can implement the file system driver in other parts of things. But I would assume, I'm pretty sure the file system is also implemented in the kernel. So just everything is like monolithically bundled into the kernel. But here they're doing everything super differently and interestingly with things in user space. And apparently the disk driver is in user space. It's easy to implement disk access in user space this way as long as we're relying on polling. Programmed IO, not port IO. Programmed IO, PIO based, and not use disk interrupts. So that's also interesting. So we are not using interrupts. It's possible to implement interrupt-driven device drivers in user mode, the L3 and L4. What is that? What is the L3 kernel? Is that some... Okay, apparently it's like some famous operating system. I think so. L4. So there's like the SEL4 kernel, and maybe that's related. So SEL4 is a kernel. L4 kernel. I think L4 is like apparently this is like some, yeah. Hand-coded assembly language in 1993 created attention for being 20 times faster than Mach. The following publication was so influential that it won the 2015 Hall of Fame. Dang. So apparently, this is like pretty hardcore stuff, apparently. So I think that's what they're referring to. So apparently they do this. You can implement device drivers in user mode. It's more difficult since the kernel must field device interrupts and dispatch them to the correct user mode environment. The x86 processor uses some bits and E flags to determine whether protected mode code is allowed to perform special device I/O instructions. Now that is interesting. I wonder if I have an E flags anywhere over here. I don't believe I do. No. Let me try to bring up my Intel manual. I always like to go to the source. My favorite diagram, by the way. We're going to look at the system programming guide. No, I actually don't think we need it. We just need the basic architecture. E flags. Oh, 20-second break to stand up and get some water. Be right back. Okay, back. So let's take a look at E flags. Let's get our E flags diagram stashed over here. And IO privilege level is what it's talking about. IO privilege level. I am completely unfamiliar with this. Indicates the IO privilege level of the currently running program. The current privilege level must be less than or equal to the IO privilege level when accessing the IO address space. Okay, so the current privilege level must be less than or equal. Right, and so our tasks run in ring 3, privilege level 3, which means the IO privilege level must be 3 if we're going to allow that to work. And that's kind of interesting though, so that's how you allow user space to directly do IO accesses, which typically are kernel only. Okay. The more you know. To determine whether protected mode code is allowed to perform in and out, since all of the IDE disk registers we need to access are located in the IO space. Giving IO privilege to the file system is the only thing we need to do to let the file system access these registers. In effect, the IOPL bits provide the kernel with a simple all or nothing method of controlling whether user mode can access IO space. In our case, we want the file system environment to be able to access IO space. We don't want any other environment, so that's interesting. So in this design, it's kind of like a microkernel, which means that it's not a monolithic kernel. So we have the kernel, and then just in terms of the diagram, we have, we're gonna have a line, the kernel, and then in user space, we have user procs. Maybe like user proc 1. User proc 2, for example. And then we also are gonna have this interesting thing called the file system server, or something like that. This is not a normal process. It's a user space process, but it implements access to the file system. And so we have the kernel, we have the hardware. So typically the kernel is the thing that I'm also going to maybe make all these lines a little bit thicker. if I can. Yeah, they're a bit skinny. I do not know how to do that. Font size, okay, never mind. But anyway, so the kernel usually accesses the hardware. But in this case, the file system server is also going to directly access the hardware. And then the user processes, instead of talking to the kernel to access the file system and the hardware, they're going to talk to the file system server, I believe, in order to do all their disk stuff, which is quite interesting. And that's, I believe this design is called the microkernel design, as opposed to a design where there's no file system server, it's just like the file system. And it's part of the kernel. And then these things talk to the kernel. So it's actually quite interesting that they choose to do this design, and I'm quite interested to try it out. So we're using this user space approach, and so the file system server is the one that has these privileges to access the hardware, but then normal user processes don't have the privileges to directly touch the hardware. And the way we control this is with IOPLL bits in E flags equal 3. Let's color this light blue. And then EO equals 0. So that's kind of interesting. The more you know. Okay, exercise 1. i386 init identifies the file system environment by passing the type, this thing, to your environment creation function. Modify mcreate so that it gives the file system environment IO privilege, but never gives the privilege to any other environment. Make sure you can start the file environment without causing a GP fault. You should pass FSIO test and make grade. All right, let's code. Thanks for bearing with me while I just read through all of that stuff. It is time to code. Create. So we're here, we are concerned with env create, right? And there's this type argument. So we have some different environment types. We have a normal user environment, and then we have a file system environment type. And we pass this into env create, which is then passed into this like macro for reasons I don't completely understand. And then we have this type. Now it's time to see how you do this. So if this is the file server, give it IO privileges. So if env type equals env type fs, then we want to set the IOPL bits to 3. So we're going to take the trap frame and E flags, and we are going to enable some bits, and what those are exactly, I don't exactly know. We need to come back here and see that they are the 13th and 12th bits. So basically I need to make a bit mask of like all zeros and then 2 1s here. So now it's time for some noob hours. If I do 3 shifted to the left, 12 bits, yeah, exactly. I think that's what we want here. Yeah. I am like a little bit just double checking like this 3. Is that exactly just 2 bits? Are there... Or does the 3 is like the 3 like an int or something like that with a bunch of extra zeros or something? But even if it is, even if it has extra zeros, it doesn't matter because those are just still zeros. So yeah, that's totally right. Is there any way we could improve this code a little bit? Also, for example, I wonder if there are some constants we can use, like in although fs.h is not included in here. So, okay, just for clarity, I'm going to take this one level further in software engineering and not use magic numbers. So I'm going to say int k user space maybe just k ring 3 user priv level equals 3, and then something like IO PL offset bit offset. Maybe that's easier to read, maybe it isn't. I think in general, I would like to avoid all these magic numbers, so I'm gonna go with this. All right, crushed exercise 1. Make sure you can start without causing a GP fault. You should pass the file SIO test and make grade. So we're gonna open up grade lab 5. And so again, I wish there was a way I can, so where does this lab variable come from? Or maybe I have to specify it. And then the grade flags. Here's where it comes from, lab 5. Okay, cool. Then the question is just like, how is there any way to lower args? Filters. So I just want to run fsio. I wonder if I can do this. Make grade fsio. I wonder if this works. Ooh, I think that did not. I think it's running some other tests I did not want. But the more so that completely failed clearly. But more importantly, it passed the one, or even did it? What? Okay. I am going to just do the dumb thing and like, oops. Comment out this stuff, which is how I've usually worked. Grade lab 5. So apparently this is not working. Why is it not working? Is there a log? No runnable info. Oh, I know. The reason is because it told me to disable this thing, so I never sent. Okay, so we need to have this thing enabled. Start the fs, and apparently there's this fs.c program, I think. This is not it. It's like some name. Okay, I don't know. I don't know where this comes from, but we need this. And so now it should work. Ten out of 10, sweet. So that's cool. So now we need this back. And more importantly, this is our patch. So, what is the commit message here? It's like, give fs user space server IO priv levels. It will be doing direct IO with the disk, but other user space procs shouldn't be able to do this. Okay, what do we do with all this stuff? So what do we do with this? Here's the, yeah. I think I'm just going to going to add this back. I don't know. Actually, no, I think I will just amend it into this commit. Okay. Cool. So that was nice. Question, do you have anything else to do to ensure that this IO privilege setting is saved? So why? So this is a part of eFlags. And what else happens with eFlags? My initial reaction is no, I don't think so. So we create this process with its register state. And then when it's time to run the process, we kind of load all this register state into the actual registers and begin execution. And these IOPL bits are not touched by that part of execution. Although it's a question, like, can user space change its IOPL bits? I would assume not. Some flags can be modified directly. There are no instructions that allow the whole register to be examined. So this is the part that we make use of. We do not use this part. So this is, we're not using the processor's multitasking facilities, but when an interrupt or exception happens, this thing just gets pushed onto the stack, and then we copy that back into like the data structures that track the process states. So I am gonna say No. But maybe I'm missing something. What would be a reason that this IO privilege setting is not able to be restored? I think it's only if user space can actually tamper with it. If that's the case, then yeah, we need to make sure that on every execution into user space that we make sure if it's the file system environment that we are setting these bits in case they somehow are changed, but I don't really think so. So the make file sets up Kimu to use the file blah as the image for disk 0 and then use this new thing as the image for disk 1. In this lab, our file system should only ever touch disk 1. Disk 0 is used to boot the kernel. If you corrupt them, you can reset them using rm and then make. Challenge, implement interrupt-driven IDE access with or without DMA. You can decide whether to move the device driver into the kernel, keep it in user space along with file system, or even move it into a separate environment of its own. So this means the device driver is, like currently we have this file system environment which contains both the driver and the file system, and apparently you could even separate those into the device driver being one process and then the file system itself being a different one, and they need to communicate. Okay, 20-second break. Quickly. Okay, and then what? The block cache. So in our system, we implement a simple buffer cache with the help of the virtual memory system. Code for the block cache is here. So our file system will be limited to handling disks of 3 GB or less. We reserve a large fixed 3 GB region of the file system environment's address space. Wow, interesting. So basically, if we accept this limitation, we can then do some certain implementation, which apparently uses virtual memory. We reserve a large fixed 3 GB region of the address space from blah to blah as a memory mapped version of the disk. Disk is mapped there. X1000 is this? Oh, block 0 is mapped there. Disk block 1 is okay. Even though the blocks are 512 bytes, we apparently this is basically wasting some space because we have block 2 at 4K. So that's wasting a lot of space actually. So maybe I'm missing something. But you could apparently it's like kind of making some equivalence between blocks and pages. So translation from disk block numbers to virtual addresses. Since our file system environment has its own virtual address space independent of the other ones, of the other environments, the only thing it needs to do is implement file access. It is reasonable to reserve most of the address space in this way. It would be awkward for a real file system to do this since modern disks are larger than 3 GB. Such a buffer cache. Okay, it would be awkward to do this on 32-bit since disks are larger. However, if you have 64-bit at a 64-bit address space, maybe it's still reasonable. of course it would take, so the super naive approach is, okay, file system server process, it allocates 3 gigabytes of memory and just like reads the entire disk into memory, which is a funny idea, like super. Wait, yeah, I mean that doesn't work. Like it's super wasteful of memory. It like defeats the entire point of having a disk basically. And also I don't think we even have that much physical memory. So of course it would take a long time. Not only would it take a long time, it would probably waste all your memory and be kind of a stupid thing to do. So we'll implement demand paging where we only allocate pages and read the corresponding block from the disk in response to a page fault in this region. This way we can pretend that the entire disk is memory. That's pretty interesting. Let me see if I can sketch it out just for my own understanding. So we have our, here we go. So we have the memory space. But also like, so we have a 4 gigabyte virtual memory space, but like the kernel, oops. Well, I cannot like draw this straight for some reason. The kernel is like up here. And then apparently there's still enough to have like 3 gigabyte mapping for disk. And then this is like file system server code stack, etc. And there's some translation from disk block to virtual address. And when we want to access a certain disk block, we convert that in the file system server to the corresponding virtual address. And then we just simply access that. That. And then that's going to page fault. But then we must set up a page fault handler to set up. It observes the address being faulted in, converts that to disk block, uses IO to fetch the disk block, read it into like allocate memory, allocate a page of memory, copy the disk block into there, and return. Something like that. Then the file system server basically just resumes, and just from the perspective of the file system server, it would just appear that like all these all these memory accesses just like work, and then the data is just magically there, like for all of these disk blocks, and they're kind of being lazily paged in. Oh. Implement the BC page fault and flush block functions in bc.c. BC page fault is the page fault handler, just like the one you wrote. It stops to load pages from disk in response to a page fault. Keep in mind that adder may not be aligned to block boundary, and IDE read operates in sectors, not blocks. Yo, what's up, Juan? Hello, hi. Thanks for joining. Okay, the flush block function should write a block out to disk if necessary. Flush block shouldn't do anything if the block isn't even in the block cache. The page isn't mapped. Or if it's not dirty. You'll use the VM hardware to keep track of whether a disk block has been modified since it was last read or written from disk. To see whether a block needs writing, we can just look at the PD dirty bit. Interesting. So we have like a disk, we have a block, we read it from disk. What about writes? So if we want to do a write to disk, we literally write to that part of virtual memory, presumably, and then at some point later, we flush things to disk, and we flush the things that have been made dirty. And so the flush operation possibly needs to iterate through the whole span and flush out every dirty page, and then mark it like not dirty or something. I kind of don't know that detail actually. Can you just write overwrite those bits in memory? Maybe. Okay. Okay, after writing the block, the disk flush block should clear the bit using sys page map. Interesting. Okay, let's do this. So this thing is like this still. So let's begin. So let's start with the page fault handler BC. So page fault. Okay, so we are here in our handler function. Yeah, inside the file system block cache, we call set page fault handler. And apparently there's a bunch of code here already. What do we need to do? So what does it do? It gets the trap frame, it extracts the address, it performs the conversion to convert that to the block number. It validates that, but it validates the address. So there's a specific region of virtual memory. Let's look at the mem layout. Disk. Oh, what? There's no disk. Okay, so this is the typical memory layout, but apparently we are diverging from this somehow. Where is disk map? Is that mentioned anywhere? It's not in the diagram. What is it? X10 million. Is that? Okay, well anyway, the kernel just for awareness, let's just see how much space the kernel has. So that's divided by 1024, divided by 1024 is 275 megabytes. This might be off by one error actually. I think it should be +1. So, but approximately 275 megabytes is for the kernel region. And right, and our whole address space is 4 times 1024 megabytes. So it's a pretty small portion of the address space. Did I do this right? Bytes divided by 1024 is kilobytes, divided by 1024 is megabytes. So yes, and then 4 gigabytes is 4 times 1024. So 1024 megabytes is a gigabyte. And we have 4 of them, so I'm pretty confident in that. Basically, the conclusion there is that we have a lot of user space, address space available. We have basically like this much, right, which is like multiple gigabytes of 3.5 or whatever gigabytes of address space. Something. Am I missing? For some reason that number seems a little bit low to me. So 1 megabyte. Alright, this is like kind of stupid math. So 1024 megabytes is a gigabyte times 4. Okay, anyway, I'm just gonna leave that there, I think. So basically, yeah, there's a lot of room here, and we are just starting from hex, like kind of like high randomly here, and going up plus n times block size from there. Disk size. Maximum disk size we can handle, 3 gigabytes. So just to get a sense of what the numbers are. Okay, so it's going to be plus 1, basically. 1 here, plus C is D 0 million. And we can quite comfortably do that. Then the only important other stuff here is where our stack is, which is in the hex E region. So that's all quite comfortable. What's up, Mohammed? Hello. Basically, okay, so checks whether the address is in the space, and then although it's kind of interesting, like this user space page fault mechanism is responsible for also handling copy on write, but we don't have a good and usually that requires installing a page fault handler. But here we have one installed that does some separate stuff. So in the current form, like we would need to compose them together to allow the FS server process to fork, basically, which maybe that is totally possible. Yeah. Sanity check the block number. So there's like this global pointer or something. So if we have super block and the block number is greater than equal to the number of blocks, we're like going out of bounds on the block number. Okay, allocate a page, read the contents of the block from the disk into that page. Hint round address to page boundary. Thank you. Okay, void. Rounded equals round down the page size. Adder aligned. Read the, okay, so now we need to map some memory. And I kind of forgot how to do that. I'm going to look at 20-second break. All right, be right back. I am going to look at a fork. Let's see. So here's our actual forking function, and it needs to do very similar things. You have this address, and I align the address. Okay. So we need to allocate some memory. Except we're going to allocate at adder aligned, and it's present user space writable memory. And then we use this IDE.C code to read. IDE read, I think, is the function we want. And I don't really understand how this works, but you can pass a sector number, a destination, and a number of seconds. Is that? IDE read, yes. What is nsec? Are there any example usages? No. Is there a header file? No documentation. That's file read. Number of seconds, maybe it's a timeout. I think it's a timeout. What is R? R is some kind of error code. Okay, return some error code. So apparently there's some like timeout or something. Not quite sure about that part, but let's try to do this. So we've allocated a page of memory. We're in user space, and we've used the system call to allocate a page of memory in response to someone trying to reach the disk. And then we're going to do IDE read. We're going to have to pass a sector number. A destination is adder aligned, and number of seconds, I'll just say 1 second. And sector number, unit 32T, sector number. What is this? So we have the block number, and Currently on the system, there's a 1-to-1 correspondence between blocks and sectors, but that might not always be the case. So we want block number. It's like times sectors per blocks, basically. For example, no, like, wait a sec, block number, yeah. So for example, if we had, like, let's, I see. So if, so right now with one sector per block, it's pretty easy. If there were multiple sectors per block, we would actually need to loop and do a couple operations here. Right. So like sector, it's like block number 2 would be like, for example, let's say you have 2 sectors per block. This is like kind of silly, yeah. So then you would multiply that by 2 and get indexes 3 and 4 are the sectors, or the sector numbers you need to access. Yeah. Both are 512 bytes each. I wonder, are there any symbols that are like sector or block or BLK? Yes, I kind of thought so. What's up, GJM Reborn? Yes, I am. Here's the link to the course. Also, Afnan, what's up? You are late. Yeah, but no worries. I'm still streaming for about 20 more minutes. So we have the block size, block bit size. So we have some constants. So I kind of want to do like a static assert or something that's the block size is the same as the sector size. I'll just put a to do comment and this will break. To do, we assume block size equals sector size 512. But wait a sec. So there's a 1-to-1 correspondence between block number and sector number. Then this is saying block size and page size, which is a little bit confusing. This is saying in Java, sectors are 512 bytes. Oh wait, whoa. So wait, I am actually misunderstanding this. Marcellus marching my chill ASMR background music and the keyboard sound can't explain how relaxing it is. Yeah, thanks. I can type a bit louder on my keyboard if that is helpful. Okay, so never mind, I am wrong. So our file system leaves a block size of 4K. So I was completely wrong here. So actually, just to draw it out, so we have 4K, which means what? It's like 8. So 4096 divided by 512 is what? 8. Okay, so then we need to take the block size. I feel like some fine sector size 512 would be nice to have. Okay, so here we're paging in one block, and to do that we will need to actually do 8 disk reads, I believe. So actually, to allocate a full page of memory, maybe I won't make this constant, I'll just make it a local const int sectors per block equals block size divided by sector size, right? And then int I equals 0, I less than sectors per block. Okay, so, right, just to quickly sketch this out. So we have our block size, block equals 4K. Then we have our sector. And it takes, for each block, it takes, oops. No, yeah, it just takes 8. It takes 8 sectors. So someone is requesting a block, this much, and to internally provide that much memory, we need to go and do 8 sector reads. So that's kind of what we're doing here. Okay, and then to get the sector number is going to be like the block number times sectors per block plus I, right? So for example, if we are trying to access the 0th block, that's going to be 0 through 7 sectors. And so 0 times 8 is 0 plus 0, 1, 2, 3. Let's say we're accessing the 2nd block. That's going to be 8 through like 15 or whatever. And so 1 times 8 plus blah, blah, blah. So we compute the sector number, and then we also need to adjust the address we are reading into. It's gonna be address plus I times sector size. And we're going to int R, and then if R panic ID read failed, something like that. So here we are just kind of like satisfying the request for a block, and we're internally deconstructing that into this number of sector reads we need. Assuming I read this right, we use a block size of 4K, conveniently matching this, we use a block size. On JOS, sectors are 512 bytes. I kind of wonder where that is defined actually. What is hex 512? Hex 200. Is there hex 200 anywhere? I'm quite interested in where it is actually defined that the sector size is 200, but I am not immediately seeing that. I mean, maybe that's just the property of the disk, as it's saying, and that's not really even in the driver. It's just kind of implied or something like that. So, oh wait, oh so wait, we do, okay, what? So so there is already a constant for, oh, blocked sex. Okay, there's already constants for all these things that I was doing, actually. It's kind of confusing that there's two fs's.h. So I don't need this. And just to do it in their terms, block sects and sect size. Okay, just to fully do it in their vocabulary, sect size, blocked sects is what they chose to name it. Block sectors. Okay, so right, so allocate a page, get the contents of the block from the disk into that page, blah, blah, blah. I think I've done that. Clear the dirty bit since we just read. Okay, so apparently we just, like, the kernel just controls this. And this page map. The last parameter is the perm. So basically just this page map handles, oh, I mean probably basically it's just, I guess it's just changing the permissions. And it's looking up the existing page table entry and anding it with some bits and basically clearing out everything else. Okay. Check that the block we read was allocated. Exercise for the reader. Why do we do this after reading? I'm going to copy this in because it's usually important to understand. Okay, then we check that the block we read was allocated. So what we're doing is we're checking if this bitmap, I don't really know what this bitmap thing is, but it's like this global data structure that describes the disk or something. And then we're confirming, and if the block is free, why do we do this after reading the block in? So we read the block into memory. I actually don't really understand what this is doing. It's like some bitmap stuff which I haven't gotten to yet. Maybe there's like some race condition or something, or was allocated. I think I'll come back to that later. I don't immediately understand what's happening with this stuff. So that is the first part of this. Page fault. Flush block is the second part. Flush the contents of the block containing virtual address out to disk, then clear this thing if the block is not in the block hash or is not dirty, it does nothing. Hint, use VA is mapped, VA is dirty, and IDE write. Use the PTE syscall constant when calling syspage map. Don't forget to round adder down. Okay, thank you for the reminders. I'll do the typical thing. Okay. We will just delete that. Flush the contents out to disk if necessary. If the content block is not in the block cache, I think I need to read VA is mapped. I think it might be important to know what these things do. So is this mapped? So the way we check if it's mapped is we take the virtual address, we get the page table entry, and we see that it is present. And we see that the page directory entry for it is present. And then we see that the page table entry. And it's important to do this page directory check because doing this kind of thing, if you try to check the page table entry directly for something that doesn't exist, that process will crash. And so you first need to check if the page directory exists, because this involves walking the page tables. Yes, and if it's not mapped, it will crash, meaning it will page fault exception as part of doing the page table walk because there is no entry here. So basically, is it mapped? So flush block. So I'm just going to make a guess. Not VA is mapped. Adder aligned. Return. Or not VA. It is dirty. But wait a sec. So we're flushing an entire block to disk. So we have all these blocks. So we read all these sectors into memory. And then here's what's happening. So either in the first case, nothing even happened to this thing, and we're being told to flush it out. Which means we don't need to do anything. We just observe that it is not dirty, so then we click return. Or alternatively, someone like wrote into this memory, and now it's up to us to flush it out. So we don't know where within this block or page it was written to. So all we can do is flush the entire thing, when in actuality, it might have only written to one of these sectors. So in theory, we only need to write to the minimum number of sectors, but we don't have that granular information. All we can see is that somewhere in this block, it has been made dirty. So the only thing we can just do is render, kind of push, write it all out to disk, even if it's redundant. Okay. So if it's not mapped, return. If it is mapped, but it's not dirty, return. Then it is mapped and dirty. So then we do IDE write block to disk 0i. I'm going to kill the palm tree because it's almost end of time. Block sects. Okay, and for each sector, do write, which is sector number, number, which is going to be the block number. It's the exact same thing times block sex plus I dir number. That could even be a helper function, maybe, might be worth it. And then we take a source pointer, and apparently it will like write 512 bytes. I guess the way this works is you send a bunch of commands or something. Is this? I don't know what this is really doing, but sector size divided by 4. So you load in the bits of the sector number somehow. You select a disk number and also the last bits of the sector number. You have this write command. You wait till it's ready and then you like trigger a write, and maybe you tell it how much you want it to write, but then we bump this by 512, which is like pretty bizarre. Even though it's const. But it's const void, it's not const on the pointer. So while n seconds is greater than 0. Apparently this takes a time or something. No, it's a check error, okay. And it like kind of counts down, and then we'll return 0 if it times out or something. It just like, so I don't really understand this thing where it like bumps it by sector size. So I am just going to assume we're writing 512 bytes, adder aligned. Plus, what was it, I times block size with 1 second or something like that. Okay. At least that's kind of what I did. And then we like panic if there's an error or something. Okay. So let me call this page map. I think we just do the exact same thing here. Clear this. And R for error. Don't forget, okay, I think I did everything here. So what we do is we get an address to flush the block of. We align that down. We also compute the block number. We validate that the address is within the range. Then we check if it's mapped and dirty. And return if it's either mapped, if it's not mapped, or not dirty. And then lastly, we write out every sector. And this is still a little bit TBD as to how this exactly works. Like, what's up with this? Maybe I wonder if there's a quick way to get more info on this. IDE, Kimu, IO port, this thing. Okay, there's people asking some questions. This all looks kind of, okay, this looks like what I want right here. Okay, and specifically X1FO. Okay, so the simple disk driver for types of registers. Control register. We have some register numbers. Data port. So let's just see if is there any possibility that these look kind of the same? Also, why is that taking so long? Okay. So F2 and oh wow, I am stupid. That is number of sectors, not number of seconds. Wow, okay, I did not do this right. I don't need this loop. IDE read supports doing multiple sectors, I guess. So you can just tell it, hey, I want to basically, I want to read n sectors from block sects, I believe. That's much easier, okay, than this custom for loop. I was trying too hard. So the starting sector number is block number, and then you do an IDE read and give it the number of sectors. And I wonder if it says that they're 512 bytes or something. Okay, maybe not, I don't know. So yeah, so here we're reading block sects from sector number into address line. And it's kind of neat that you just pass pointers. So there must be some kind of DMA I think, I don't actually know, but that's what I am assuming. Like if you can pass a pointer into like to the device, and then the device can put things into memory for you, I'm assuming that means the device can do DMA. So let's let's fix this thing. So in the same way, I don't need to do this. I can just and then it's block sects. Okay. And I'm writing, this time I'm just writing block sects from sector number from adder aligned, and then clearing things. So I need to go, but I'm curious if there's some way I can test this. So we should pass a couple of things now. Check BC, check super, check bitmap. Let's go into grade lab 5 and enable these tests, and let's run it up. It's probably not going to work, but oh, okay, compile error. Adder R was already declared. Okay, let's try it again. Okay, that all worked. So I would call that a success for today, y'all. Finished exercise 1 and 2 from lab 5 of the file system lab. And apparently, I don't know how much longer this thing is, but it doesn't look like a super, super long lab compared to lab 4. So, I mean, that's just because they wrote a lot of the code here, I guess. So, yeah, that's gonna be it for today. I want to thank you all for joining the stream. Here's my Discord if you want to keep in touch. Please subscribe to my channel if you enjoy this kind of content. I'm here every week. And I'm going to leave it here. Next week, we're going to pick up right off with this and get into the next parts of this lab. So feel free to join for that too. All right, y'all. Have a nice week. I'll see you next time. Peace.